Okay, so what we've got here, I'm going to take some problems from the mixed gas law worksheet that we got last Tuesday, and I'm going to solve them and show you my work so that you can see the thinking behind them. And I've chosen three of the what I thought were more challenging problems, and hopefully if you were struggling at all with this worksheet, this will give you a better idea of some tactics on solving these types of problems. Okay, so the first one I've chosen is number 11. It says gas canister can tolerate internal pressures up to 210 atmospheres, and if you had a 2-liter gas canister and it had 3.5 moles up at 13,500 Celsius, is that going to cause that canister to explode? And in this case, I chose this problem because it's asking you to make an evaluation. It's not just asking you to do a calculation. You have to do a calculation and use that information to make a comparison. And in this case, you're comparing a pressure. So the pressure they tell you that the gas canister can tolerate, this is the key, is 210 atmospheres. So don't be confused by the fact that they gave you that number. That is not technically a given in this problem. If we plug 210 atmospheres into our PV equals nRT, we're going to get something else. All right, what we need to do is plug in all the other givens and see if they add up or multiply up to 210 atmospheres. And if they do, then we've built up too much pressure. So we're looking at the other givens here, the other stuff. That's just the rating on the canister. So I'm going to write down a few givens here, and I'll underline them so you can see. I look and I see 2 liters, and I see 3.5 moles, and I see 13,500 Celsius. So I'm going to put those down here. The 2 liters, I know that to be a volume. The 3.5 moles, I know that to be N for number of moles. And the 13,500 Celsius, I know that to be a temperature. And I know I'm also going to have to need R, because the ideal gas equation has a constant in it that is 0.0821 liter atmospheres divided by Kelvin moles. And right away when I write that, I look and I see some of my units don't match. For instance, I do have liters and I have liters, that's good. I have moles and moles, that's good. But I have Celsius over here, and here I need Kelvin. So I need to make a change. So I'm going to go back here and change my Celsius. That was 13,500. I need to add 273 to that to make that Kelvin. So 13,000, whoops, let's change that back to black. Okay, that was 13,500 plus 273 would be 13,720. No, 73. Excuse me. I can math. Yes, Kelvin. Good. And now I see the Kelvin will match right there. And I can plug everything into the ideal gas equation. So PV equals nRT. Pressure is what I'm solving for, so I'll leave that as an unknown. Volume I know is 2.0 liters. I'm going to leave out the liters because I know they'll cancel. I underlined that. 3.5 moles times 0.0821 gas constant times 13,773. Okay, and now if I plug that into my calculator, so I'm basically going to take these guys on this side. Whoops, let's not do that. I'm going to take these guys and divide them by 2.0 on both sides, and left over I should get 1978.8357, etc. It goes on. Now we're obviously not keeping all of those digits, so let's figure out what we are keeping. If I look at my givens, I see this is 2 sig figs. I see this is 2 sig figs. This is 5 over here, and that's 3. So the amount I'm keeping is the smallest number of sig figs. So I should be rounding to the second significant digit. And so in this case, my final answer should come out to 2000 right there, or 2.0 times 10 to the third. And that would be in atmospheres, because I'm looking for a pressure. So 2,000 atmospheres, or 2 times 10 to the third atmospheres, if I've done my calculations correctly. And now, that's not the final answer. If this was a test and I wrote that down, I would have gotten a number that was probably the number I was intending to calculate, but I didn't do the final step, which was answer the question. The question said, will the canister explode? And if I don't say yes or no and base it on my math, then I'm not answering that question properly. And we saw at the original point it was 210 atmospheres right there. That's what's going to cause this canister to explode. And clearly I've hit 2,000. And that's way too big. Too much. So I'm going to have to say, yeah, this canister is toast. It would have exploded long before it got to 13,500 Celsius. Okay. All right, now we're going to go on from there, go to the second one. So our second problem here, this is a change problem. So it says an airtight container with a volume 4.25 10 to the fourth liters and an internal pressure of 1 atmosphere and a temperature of 15 Celsius gets washed off the deck of a ship, sinks to a depth where the pressure is 175 atmospheres and the temperature goes down to 3 Celsius. What will the volume of the gas be when the container breaks? So this container is going to fall into the ocean, fall down to a very great depth, and break because the pressure crushes it. And that gas on the inside, which we assume must have been a non-flexible container, which was keeping its volume up until that point, will now be squeezed by all of that water, and its temperature will change. We'll see if that changes its volume. It should. So I'll start again with givens. I look like I have liters, atmospheres, Celsius, atmospheres, and Celsius. And key words here, all right? Is washed off the deck of the ship and then sinks to a depth where the pressure is. So I have initial conditions and I have final conditions. So I'm going to indicate that with my numbers. So my first one, 4.25 times 10 to the fourth liters. I know that's a volume. And it happened before it got washed off the deck, so I'll say that's volume 1. I also have the 1 atmosphere, which is also before it got washed off the deck, so that is pressure 1. And I have the 15 Celsius, which was temperature 1. After it was washed off the deck, I have 175 atmospheres, which is now going to be pressure 2. And I have 3 Celsius, which should be temperature 2. Those are all my givens. I'm going to go ahead, knowing what I know, that Celsius does not work as a temperature for gas laws, so I'm going to get rid of that and add 273 to it. So 273 and 15 would go up to 288 Kelvin. And then I know 3 and 273 would go up to 276 Kelvin. All right. Now, the reason I chose this problem is it is a change problem, but it has 3 variables in it, 3 different types of variables instead of 2, which is a little more challenging, but still plenty doable, as you'll see. So I tend to forget my relationships, whether they're direct or inverse. So here's how I do it when I want to find those relationships again. Oops, get rid of that. I will write my gas law out, PV equals nRT, and I'm just going to try and isolate all the variables that I know are part of this problem. In this case, pressure is a variable, volume and temperature are also variables. So I want to get those, I'm going to isolate them on the same side of the equation. I'm going to get, PV is already over here, but I need the T over there as well. So I'm going to divide by T on both sides. get PV over T, and that will cancel the T's on the right, so let me get rid of that. So what I find then is that PV over T equals NR, and NR in this case should be a constant. R is certainly a constant, and N, the number of moles, should not be changing. It was a sealed canister and it sank, so all the way down there were the same number of particles in there, and then the container breaks, and until those gas particles leak out, they should all still be there. So we'll say that NR is a constant, meaning I can rewrite this as P1 V1 T1 equal to P2 T2, oops, V2 T2. All right, and that from this point on, you're just plugging in numbers. So P1, pressure 1 was 1 atmosphere. And if atmospheres and atmospheres are the same, I'm just going to assume that they cancel. Same with Kelvin here. So 1 atmosphere times 4.25 times 10 to the 4th over my Kelvin. Temperature 1 was 288 Kelvin. Equal to my pressure 2 was 175. Ouch, that's pressure. Times V2, that's my unknown, over T2, which is 276.000. Okay, and I'm going to plug that into my calculator and solve it. I'm going to have to multiply by 276 from over here. So multiply by 276, and do it over here, 276. I'm also going to have to divide by the 175, so 175 here. So this expression should give me my new volume. And plugging that into my calculator, I get 232.738, etc., etc. And again, I have to go back and do my sig figs. So if I look, sig figs, I've got 3 here, 3 here, 3 here, a bunch. So it looks like 3 is my limiting because temperature has a bunch of sig figs. So coming down, I'm only going to keep the first 3 digits. So 232, but I'm going to round that to 233 liters because this is a volume. So it definitely went down. I mean, if you look at my original volume, I had 42,500, and I'm now down to 233. All right. Last one, and I've gotten a lot of questions on this one. 2 flasks connected with a stopcock. Flask 1 has a volume of 2.5 liters with oxygen gas at 0.7 atmospheres. Flask 2, 3.8 liters, hydrogen gas at 1.25 atmospheres. So I'm going to draw this. Here, it doesn't matter what you make your flasks look like. They just have to be 2 containers. Okay, stopcock in the middle. Some barrier that keeps them from mixing. And if this is, so we'll say this red gas is here, and we'll say this blue gas is over here. And we can further say we had volume over here equal to 3.8 liters and pressure equal to 1.25 atmospheres. And over here the volume was equal to 2.5 liters. And the pressure is equal to pressure is equal to 0.7 atmospheres. 70, I should say. The important thing here is that these are ideal gases. And if they are ideal gases, they are not interacting with each other. So once I mix them, they will both occupy both flasks, but they will also both push on the walls, and the fact that there's another gas bouncing around in there with them will not affect one gas's pressure or the other gas's pressure. So the blue gas, if it was going to fill up, say, and have a new pressure of 0.5 atmospheres, and if the red gas had also a pressure of 0.5 atmospheres, those aren't hindering each other in any way. That's what allows us to do this problem. So I'm going to go ahead and do this. I am going to solve for just this set of data. This is a P1 V1 situation. All right? And once I open the stopcock, that gas is going to expand from this chamber into the whole two chambers. So it will now have a new pressure and a new volume. It'll primarily have a new pressure because it has now a new volume of space. And I'm only going to consider this gas right now. I'm not going to bother with the other one. So this gas right now has a pressure of 1.25 atmospheres and a volume of 3.8 liters. But once I open the stopcock, it now has both chambers to bounce around in. Well, one chamber was 3.8 liters, the other chamber was 2.5, so together it should have a combined volume of 6.3 liters. So I now should be able to calculate its pressure if I do 1.25 times 3.8 and divide it by 6.3. So when I plug that in, I get 0.753968, etc., etc., etc. And if I look, 3 sig figs, 2 sig figs, 2 sig figs, I should be rounding to here. So I'm going to have something about 0.75 atmospheres. But that's for the left-hand side gas, the red one. The right-hand side gas also is going to exert its own pressure. So I'm going to do a separate calculation for the right-hand side gas. It looks exactly the same. PV1 will equal PV2. So, but its initial pressure is not 1.25 atmospheres, it's 0.70 atmospheres, and its initial volume is 2.5 liters. That will be equal to its new pressure. Now, its volume, however, since it's going to be filling both chambers, is also going to be a new volume of 6.3. So now I can solve this one. If I divide by 6.3, and I should get 0.27777 on forever. So this is repeated. New pressure, atmospheres. Okay? And again, 2 sig figs, 2 sig figs, 2 sig figs, I'm rounding to here. So this would be about 0.28. This would be about 0.75. And both of those gases, those two pressures, are pushing against the walls. Well, if you're a container and you have a gas, one gas pushes 0.75, the other pushes 0.28, you feel both of those. So the total pressure on the inside of that container is going to be just over 1.03 atmospheres. Now, I want to make a note here. This was a 2 sig fig answer. This was a 2 sig fig answer because they were being multiplied. So when you have a problem like this where everything is being multiplied or divided, you always keep the lowest of your total amount of sig figs. But then I took this number and I added it to this number. In that case, you always keep the least precise sig fig in that case is the one that's furthest to the left. Now here, this sig fig is in the hundreds place. This sig fig is in the hundreds place. So adding and subtracting, I will keep the hundreds place. So my actual final answer is accurate to the hundreds place, which means it almost looks like I gained a sig fig, but that's for adding and subtracting. So for adding and subtracting, you can keep that hundreds place unless there was a less precise number. So if this was like 0.28 plus 0.7 and this was accurate to the tenths place, then I would have to keep only the tenths place in my answer. Okay? So 3 problems from the problem set. Hopefully you learned something.